I don't know how to count. 1, 1, 1, 1. Wait, that's not correct. Since what I'm holding up right now in my hand is distinct from previous counting. Surely I can't call it 1. There must be some symbols we can use before I run out of fingers to represent how many objects I currently observe. Finger 10. Start count. 0. Increase. Caution. Max. 11. How? Max right. Symbol. Start again. Increase. Realize if repeat symbols run out may be same cause confusion. I know like system need be better. I would like to introduce you to the positional notation. The digit in the corresponding position holds the value of the digit itself multiplied by the exponential value of each respective position of applied base. This prevents confusion and memorization of learning new symbols as a substitute. Look at this number. We know this number is 8,250, but we can deconstruct this number with positional notation in base 10. There's a pattern based on the position. The first digit is what we call ones, second tens, third hundreds, and fourth thousands. Let's break it down one by one. The first digit contains 0, as 0 multiplied by 1 is 0. The second digit contains 5 multiplied by 10. Check the previous video to know how digit cycles. Basically, the first digit has gone 5 cycles, and it will apply to all continuing digits. The tens place has gone 2 cycles, and the hundreds place has gone 8 cycles. We see the last digit as known as the leftmost position of the number multiplied by 10 to the power of 3. However, there are 4 digits. This is important for the formula later. To make it clearer, let's switch to another base. I'll use base 2. We'll get random number that consists of zeros and ones. Deconstruct this number using the same notation. The ones and the zeros are the digit, and 2 is the base. There are 6 digits, and the last digit is multiplied by the base to the power of 5. This means that the digits are multiplied by the base exponentiated by how many digits there are minus the position they are in. The formula can be constructed like this. I know this looks scary, but it's actually simple. N is the amount of digits, B is the base, and A sub n is the digit in their respective position, which is limited by how many unique numbers there are in the base. This is how we can get any value from any base, and the yield is in the way how we usually count, which is base 10. Let's take the previous number in binary. We can input this number in our discovered formula. 6 digits with base 2. Here's the rundown. Therefore, 101011 in base 10 is 43. You might also wonder how we could convert base 10 to another base. We can continue from the previous video discussing about division, which is just repeated subtraction. When we divide a number with its factor, we expect no remainder given, because the repeating subtraction method would never result a negative integer, and it always ends on 0. However, if the number is not divided by any factor of the number, it ends on a positive integer that couldn't be subtracted anymore, which otherwise resulted in a negative integer. The positive integer said is the remainder. Remainder is very important as it is one of the foundations of how to build a number around the desired base. Let's do the division method to convert base 10 number to base 3. I'll take a random number, divide this number and take the remainder, which is 1. Divide the integer without the fraction and repeat until the number is lower than the divisor. The first remainder is the rightmost digit, which is the first digit. We continue until the remainder in the remaining fraction, which is the last digit. So 64 in base 3 is 2101. We can check if this is true by using the formula again. Another way of converting base is addition. I want to convert 482 to hexadecimal, which is base 16. We compare what the highest number we can achieve with exponential of 16, which is close but not greater to 482. It is 16 to the power of 2, which is 256. We can figure that the hexadecimal number has 3 digits, since the highest number we can achieve is the base to the power of 2, leaving 16s and 1s for us to discover. Subtract 482 with 256. Then, we divide 226 with 16 until it is less than 16. Also, ignore the remainder. We got 14 of 16s, which in hexadecimal system represented with E. The remaining number is the last digit, which is 2. Therefore, the hexadecimal number of 482 is 1E2. Let's work backwards again. You might be wondering how to convert E. We only need to substitute it based on what the value it holds. E represents 14, so we can change it like this. And that's how we convert bases to bases. This applies to many kinds of technologies that are advancing to this day. From binary to hexadecimal, the platform you're watching this right now uses that in computing and graphics. See you in the next video.